All right. So yesterday we started talking about residuals, right? And if I asked you guys to describe what a residual is for any given point, what would you say? It's the distance from whatever line of fit we have. Okay? So it's the distance, because it's actual minus predicted. In order for it to be predicted, we need to have an equation, like an alinear equation that we do. Okay? All right, so we're going to learn about a graph called a residual plot, okay? Now, I think it was in here that we started kind of talking about, I can't remember if it was with one of you versus all of you. If I gave you guys this scatter plot, very clearly curved, yes? Now, if I plotted the means of each x and y, are you guys with me that this would look like a really positive, like a really strong value for R? Is everybody comfortable with that? R measuring the linear relationship. Is this relationship linear? And in fact, this is the best measure of that relationship in exponential. Okay? All right. So R doesn't tell us if a model fits our equation. So we need to have because like R, this would still have a very strong positive R. It doesn't tell us that it fits the equation. It says if I made a line, the line would be decent. But the line isn't the best model, okay? So if we want to decide, is a model an appropriate model, we're going to look at a graph called a residual plot, okay? So if I were to make a residual plot of this particular data set, if I think through this point, what do we know about that point right there? What do we know about its residual? It's slightly below the line, so its residual would be negative because the actual minus the actual is the point. Yep, everything below the line has a negative residual. Okay, so what a residual plot does is it keeps the x-axis the same, but the y-axis becomes the residual for a point instead of the actual value of that point. Everybody with me? Okay. So all of a sudden, that point that I just highlighted might be right about here. And then the residuals for these 3 points might be here, here, and here. Is everybody with me? So this point is still a little bit below the line. This is barely above the line. This is a lot above the line. Everybody seeing this? Okay. And I can do this for literally every single one of these points. I'm going to get a graph. Extrapolation, let's, with my line of fit. What can we say? We're going to pretend this is the line of best fit. Technically, it's not. It's close, but it's not. What can we say about the residual of all the points above the line? Positive. What's the residual of all the points below the line? Negative. So, if I add them all up, what should I get? 0. Everybody comfortable with that? And in fact, could I like find the residual for each point and make a dot plot of those residuals? Yeah. This guys looks a lot like this one. Yeah? Is everybody good so far? Okay. Now, what do you guys see in this graph? Do you see any patterns? That's a good thing. Okay, and this feels wrong. But if our line actually models the points, shouldn't the points be equally scattered about the line? Do you guys see what I'm saying there? Okay. So remember, this graph isn't the line. This is the relationship of the points to the line. Okay? So, residual plots. We can say a model is appropriate if there isn't a pattern on the residual plot. Now, I'm going to draw that same scatter plot we just said was curved. If I had to sketch a line of fit, it would be roughly here, yes? Give or take. Let's sketch that residual plot. What can we say about the residual of this point? Positive by a pretty large margin, yeah? So it might be right here. What about the next point? Slightly below. And the next points? Both similarly below. Slightly below, above. You guys, is there a curve pattern on this graph? Is it a lot easier to see the curve pattern on this graph? Okay. Now, like I said, it was curved. We described it with an exponential. That's not a very good. But in exponential, I could draw a smooth curve that looks like this. Start thinking through what would the residual plot be in relation to that blue curve. They'd be a lot closer to the line and they'd still be scattered. Equally scattered, okay? So residual plots can tell us if a relationship is appropriate or not. The linear one would not be appropriate because the residual plot shows a pattern. So residual plots, super important. Some other things we need to look for in our, some potential problems with residual plots. All of these would be bad. Certainly we have the curved one. It usually happens in certain types of relationships. So this is a bad residual plot. If this happens, it means the model is not appropriate. Sometimes we can get some that look like this. Where there's clearly an outlier that's pulling on the line. Sometimes, and this would have to be super prevalent. This looks good so far, doesn't it? No pattern. If you start to see that one end is more spread out than the other, that is also problematic. So they should be about the same in variability about that x-axis. Those would all make us question a model. Okay. So, again, if a model is appropriate, we don't see a pattern. And that feels icky to us because human beings are built to seek out patterns. That's what we're supposed to be doing. Okay? But if the line fits, there's actually not a pattern. Everybody good so far? Okay. Next, I'm going to switch over to something on my computer. This next part, guys, you don't need to write anything down. You just have to understand conceptually what's going on. Okay, so right now, I have this exact same scatter plot that we've been working with. How are we feeling so far, okay? All right, so I could have plotted a line on this. So I'm going to add something called a movable line. Currently, the equation of the line that's on here is 1.26 letters plus 4.05. And I could even turn this into the one we were dealing with yesterday, which was 1.5 plus 1 letters, and then plus 1.9. Does that sound right? Mm-hmm. We can see the exact picture, and this is what I used to create the scatter plot in your notes. Are we feeling good? All right. And how did we decide, is this the best fitting line we could have done? Does this look like the best fitting line? I already tell you that when I created this line, I did exactly what I just did, which is add this line and kind of adjust it. So, do I know, this was at 1.9 and now this is at 1.2, or at 2. Is it better if I have the line here or here?
Lower.
You want it to be lower? Like this low?
No, just like
Well, okay, so we're good that this is not a good line? Okay, great. And what about here? That's not good? Tell me when to stop.
Half of them below and half above.
Okay, so let's start with, in order for that to be true, I could do that. And I still have half above and half below. Yeah?
Half to below.
This is starting to feel a little bit more like, ugh. Because as I move the line, it's moving, I don't know, closer to some points and further away from the other points. Are we comfortable with that basic premise so far? Okay, lovely. All right. So how do we decide what makes the line the quote-unquote best fitting line? And that answer comes with a lot more questions than we have answers. Okay? So let's start with right now. What I did is do something called the residual squares. Lots of squares on here now, right? Okay. If I look at this square, what is the side length of this square? It's that distance, yeah? What's the word we learned for this distance? So this is the residual. So the area of this square is the square of the residuals, of that residual. And so this one's relatively close to the line, so it's a really small square. But if I look at, say, this point, this one has a really far away from the line, so it has a really big square. How are we feeling so far?
Wait, residuals don't have anything to do with R, right?
No. Tangentially related, but don't worry about it. Okay. All right. So as I move the line, what's going to happen to the squares?
Bigger and smaller.
Some of them are going to get bigger, and some of them are going to get smaller. Are you with me that the best fitting line should make the area of those squares the smallest? The total area. Does that feel okay?
Mm-hmm.
Okay, so I can move this line, and notice what it gives me, the sum of the area of these squares at the bottom. So my goal is move the line in such a way that I make this number as small as possible. Cool? So let's see, what's the first? I might say, I don't think the steepness of this line is good. Do you? So I've already got it down into the 270s from 300. And now it looks a little bit too low. Oh, 270. Oh, 267. Are you guys seeing how these small differences, they change? Some to get bigger and some to get smaller, and we're really looking at that combined area to make this as small as possible. Is this okay? All right. So we have a special name for the line of best fit, at least the one that we're going to deal with. The name of that line is called the least squares regression line. Do you guys understand why we might call it least squares? Because it's the line that makes the squares the smallest. And I can actually plot that exact line, and we can see, I'll pull out my movable line. Now we can see the line that makes this the smallest, the best fitting line. Everybody good? Okay. I'm going to do a couple of other things here. Okay, so remember how we kind of started thinking about the axes with our x mean and our y mean? Do you guys see this? What this is the mean number of letters. This is my mean scramble score. What can you tell me about the intersection of those two lines? Of the. Do you guys see how the mean goes through that point, or the actual line of best fit goes through that point? Everybody comfortable with that? And if I had, say, a different point, let's say one of these points I was miscalculated and I moved it. Do you notice that the means also change with it? And that so the best fitting line always goes through at the point x bar, y bar. We good with this idea? That it's going to contain the point that is the means of x and the mean of y. All right, what happens if I take this point and make it really big? Do you guys see how the slope is changed a lot by moving the points like outliers? Okay? Whereas if I move a point in the middle, it doesn't change the slope very much. Okay? All right. Now, so we're going to start talking about the least squares line a ton, and there are some ways to help us calculate it. So let me switch back over to this. Okay. So we abbreviate the least squares line, the LSRL, least squares regression line. Do we understand why it's called the least squares line? It makes the total area of those residuals the least. Okay? All right. So some facts. It goes through the coordinate pair that is x bar, y bar. When we move the different point around, the least squares line always was at the intersection of the two means. The two means always were on that line, okay? All right. The slope is always equal to r times sy over sx. So, now you guys, sy is the standard deviation of all the numbers that are y coordinates. In this case, it would be the standard deviation of the Scrabble scores. Does that kind of standard deviation is all about spread, so sy in some respects is kind of like the change in y. Over sx is kind of like the spread of the x's is the change in x. So if r is positive, the value of the slope is going to be positive. If r is negative, the value of the slope is always going to be negative. That's going to come into play in a little bit. We can find the y-intercept by doing the slope times x bar minus y bar. The odds of you having to use either of these two formulas is very, very slim, but they will be on your test if you need them. They'll be on the answer sheet for the test, all the formulas that you might need to use. Okay? All right. Tomorrow, I will show you Thursday, I will show you how the calculator finds these lines for you. Okay? When you put stuff into the calculator to get line of best fit, it gives you the least squares line. Okay? All right. Now, go back. So I have it. You guys, as I am looking at this, based off of what the computer said was the least squares line, we have a new equation. Everybody good? Okay. You guys, there's two numbers in my line. Which one of them's the slope?
1.464.
How do we know that the slope is equal to 1.464? Say that one more time. Okay. So why does that make the 1.464 the slope?
There's two variables.
What do you guys know about lines? Go all the way back. First time you've ever learned about lines. What's the first thing you think of when someone tells you what's the equation? Like, what do we know about lines? Y equals mx plus b, yes? And the slope is always the m, right? So, like, for instance, in y equals 3x plus 2, the slope is the 3. And are you guys with me that we called a number in front of a variable a coefficient? So in some respects, we can say that the slope is the coefficient of the x variable. Everybody good? So in this case, I might call it the coefficient of letters. What's my y-intercept? It's the 2.35. How do I know that's the y-intercept? Because it's the number by itself. What's the math word for a number that doesn't have a variable attached to it? It is a constant. This is going to come into play a lot in about a few minutes, depending on if we get there or not. Everybody good? All right. We're going to focus on slope just a little bit more. Are you guys comfortable if I say that 1.64 is equivalent to 1.6? That 1.464 is equivalent to 1.464 over 1?
Yes.
Okay, tell me, and we know that's the slope. What else do you think of when you hear the word slope? Rise over run. Sometimes I'm going to call that change in y over change in x. So which number goes with my change in x? The 1 or the 1.464?
1.
The 1. So the change in y is 1.464 when the change in x is 1. We comfortable with that? Lovely. And well, shoot. Instead of saying change in y, because I'm going to have to interpret this in context, I'm going to call that the change in score over the change in letters. Do you guys see how we got to here? If you can get to here, the interpretation's not so bad. For every one letter increase in last name, the Scrabble score is predicted to increase by 1.464 points. It's important that you use that word predicted, because it's not actually going to go up by 1.464. It's the same, you use the word predicted there the exact same way we don't say something is normal, we say it is approximately normal or approximately symmetric. Okay, the same idea, we try to use non-deterministic language. Okay, you guys, what do we know about y-intercepts?
They don't change.
They don't change? What else do we know?
See now, difference from the y where it starts. So it's the line that we were just talking about. Wait, never mind.
Yeah, I think you're thinking the right thing, but the wording is what do we know about every single point that is a y-intercept?
The y values, wait, the x value.
The x value is 0. The y-intercept is the point that is on the y-axis. And what do we know about every single point on the y-axis? The x-coordinate has to be 0. So this point 0 is actually the point 0, 2.35. In other words, when x is 0, y is predicted to be 2.35. It's not going to make sense, but what does that mean in this context? A person with no letters in their last name. Is predicted to have a Scrabble score of 2.35 points. Now, does that make sense? Of course not. The y-intercept rarely makes sense. That's not to say you won't have to interpret it. It is unlikely that the College Board will make you interpret it, but I have seen it, which is why we're discussing it. You will absolutely need to understand slope, being able to interpret the slope. No question. That will show up. Y-intercept doesn't always have meaning. So remember how we talked about interpolation and extrapolation yesterday? You guys. All right. Do you guys feel comfortable interpreting R? Do you feel comfortable interpreting R squared? If I tell you that R squared is 50.7%, would you guys be able to know to interpret what that means? Prove it. Not what is R, just what does R squared equaling 0.507 or 50.7% really mean?
50% of the variability in
50.7% of the variability
in number of letters and in Scrabble score.
in Scrabble score.
And explained by the linear relationship of the letters.
Okay. You guys, let's go back to that equation of the best fitting line. If I asked you what should the sum of all the residuals be, what would you say?
R squared.
Here's my scatter plot. So imagine here are my residuals. What's the center of those residuals going to be then? Well, we'd have a few negative residuals. We'd have a few positive residuals, right? Theoretically, there might even be like a few that are really far away from the line and some not, right? The mean of those residuals is 0. You guys, what does it mean if a point has a residual of 0? It's on the line. Okay, great. So I'm going to put kind of just like on the side here. The mean is on the line. The mean of our residuals then should be on the line. Okay, so what would the standard deviation of this graph represent? Well, standard deviation is average distance from the mean. Are you with me? Then that the standard deviation of the residuals is the average distance from the line? Since the mean is the line? Are we comfortable with that jump? So the standard deviation of our residuals is actually the average error in prediction. Everybody good? Okay. So I will typically give you S. So let's pretend that I gave you, this would be given to you somewhere, that S is equal to 4.8. If that were the case, to interpret that value, we would say the average error in prediction, or the average prediction error, is 4.8 Scrabble points. Okay. S is the standard deviation of the residuals. Here's how. Okay. Lastly, you kind of got a feel for this on the quiz, but you guys were fine because all you needed to find from something like this was that R squared. Okay? Now, what I want to do is give you an example of one of these tables and ask you, how do we find the equation of a line from one of these tables? So, for example, on your quiz review, the blue sheet that you guys were studying, the old one, that had like fuel consumption in railroad cars, right? There was a box that looked a lot like this one. That means there's a line of fit for this. Okay. Now, I want to go back to what we said about lines. For example, 3x plus 2. How did I know that the 3 was the slope? Because it was the coefficient of the x term. Yeah? This is the box for that equation I gave you guys at the beginning, or for that scatter plot of my running times and heart rates. You guys remember that scatter plot? This is the box that goes with that. Everybody with me? Does anybody see where I might find the coefficient of the x variable? But a reminder, my x variable was pace. What is the coefficient of the pace? Negative 10.53. What's the constant or the y-intercept? It's the 255.6. So if I give you one of these tables, the equation of your line, well, let's see. My heart rate is equal to negative 10.53 times, pace plus 255.6. And so, and most likely, if I ask you for the equation of a line or to do anything, I'm going to give you one of these. Or something similar to one of these. Again, if you look at your quiz review, you'll start to see that. We feeling okay? You guys, what was the R for this then, based on what we know here? This is, by the way, a trick question. Are you comfortable if I say r squared is equal to 0.856? We do have to change that back to a decimal before we do this. So what does that make r? 0.925. Raise your hand if you agree with 0.925. Does anyone disagree with 0.925? Luke, are you disagreeing because I'm doing that very obvious teacher tone that says that there's something wrong with the 0.925, or are you disagreeing because you know what it really is?
I just put my calculator in there.
Put what in your calculator? You went back and put, I want you to think about this real quick. We take the square root of both sides, yeah? When you take the square root of both sides, there are two possible answers. Both the positive and the negative of that 0.925. Now, it is not both. So how do I decide, is it positive or negative? Yeah.
Depending on the graphs, positive or negative.
Well, I just gave you this. The slope. If the slope of the line is negative, that's negative for you guys, right? If the slope is negative, then it's a negative relationship. If the slope is positive, so you have to use the slope to make the determination that this is negative 0.925. I would like you to get in the habit of writing the plus or minus and then making a decision, so that, because 100%, if they're going to try and trick you in this unit, that's how they do it. 100%. That is the easiest way for them to trick you guys. Is everybody okay? All right. We're not going to do anything about departures from linearity until after the quiz on Friday. So here's where we are, you guys. We are through 95% of Unit 2. In fact, I'll have to double check the test, but I don't think I have anything from 2.9 that is there. That is on the test. Okay? So where we are for you guys right now is all the progress checks are assigned. I know that it felt like a lot of information today. We had residual class. We had lots of interpretations. You do not need to have those interpretations mastered today. You have some time to work through. I recommend you start doing some of those practice assignments on AP Classroom, as well as the quiz and the homework, to make sure you're at this, so that next week when we're studying for the test, you are in much better place. Is everybody with me? I think your test is a week from Thursday. I haven't looked at the calendar recently, but I'm pretty certain that your test is a week from Thursday.